Good afternoon and welcome everyone to our fourth YHS India webinar titled Principles of Complex Systems in Hydrologic Inference. Before proceeding with the lecture, let me give you a brief introduction about the speaker. Dr. Pankaj is Inspire faculty at the Department of Hydrology, IIT Roorkee, and he was also a faculty at Civil Engineering Department, NIT Sikkim. He has obtained his PhD degree from Indian Institute of Science, Bangalore, at Civil Engineering Department, and further, he obtained his master's degree in Land and Water Resources Engineering from IIT Kharagpur. So, without further delay, let me hand over the mic to the speaker. Uh, Professor Pankaj, the floor is yours.
Thank you, Abhinesh. Am I audible?
Yes, sir, you're audible, very clear.
Okay. Thank you, Abhinesh, for the kind introduction. Hello, and everyone. Today, I will be talking about principles of complex systems and how we can use them to interpret temporal properties of hydrological processes. So, first, what is complex systems? So, there is no formal definition of a complex system. However, in general, we can define complex systems as systems composed of many interconnected and interdependent elements, where the interactions between these parts leads to emergent behavior. These emergent behaviors are not easily predictable from the behavior of the individual components. Complex systems often exhibit nonlinear dynamics and adaptation to external changes, and it has a tendency to evolve over time. Let us see some example of a simple system and how it is different from a complex system. A pile of stones, a pile of stones can be is a simple system because it is nothing but the summation of the properties of individual stones. Okay, so whereas a complex system, it is a much more organized thing. For example, we in a vehicle, we can see there are different components. For example, there is an engine, there is a transmission system, there is a battery, there is a gearbox, and everything. So when these systems are connected and operate in a specific manner, we get a global functionality of a vehicle. So from here, we can see that simple systems are the system which are just sum of the individual parts, whereas complex system is more than the sum of the individual parts we have. Now, catchments, which are the basic unit in hydrologic research, can be perceived as a complex system because it always interacts with different hydrological as well as meteorological processes. For example, soil, geology, vegetation, and river network. These interactions provide a distinct signature to the temporal dynamics of the stream flow. There are different aspects of temporal dynamics of a stream flow, and one of the aspect of that temporal dynamics is the memory, which we technically known as persistence. So the memory of stream flow is quantified based on Hurst exponent, which measures the decay of autocorrelation function. So basically, there are three states of persistence. First one is the anti-persistence, where the high flows tend to follow a low flow systems. There is a random system where there is no such predictability or ordering of stream flow takes place. And there is a positive persistence system where high flows tend to follow high flows and low flows tend to follow low flows. So these three classes can be divided based on the value of Hurst exponent, which is given by h. So if the value of h is less than 0.5, then we call that the system is anti-persistence system. If the value is close to 0.5, we call the system to be a random system. And if the system is greater than 0.5, we call it as a positive persistence or long-term persistence system. Now the question generally comes, why persistence or the memory of a system is we should worry about. So in this figure, we can see the annual minimum flows of Nile River over 1300 years, and this horizontal blue line shows the mean value of the minimum stream flow. So if we look at this specific time windows, we can see there is a consistent period of time where the flow remains below the threshold or below the mean flow, and also there is a consistent period of time where the flow remains very high to the normal value. So this clustering of the low flows and high flows, these are basically due to the impact of memory or the hydrologic persistence. Now the hydrologic response during high flow condition will be very significantly different than the low flow condition, because the mode of interaction between the climate and the catchment components will be different between these two states. These states impact the design of hydraulic structures, as the return levels are the functions of the frequencies of the wet and dry state. Another reason why memory matters, it influences the estimation of the return periods and its associated risk. Here is an example of the hourly rainfall datasets of 38 years with more than 10 to the power 5 data points. The Hurst exponent of the data is around 0.6, which indicates that the series is long-term persistent. In classical extreme value theory, when the value of the block maximus, that is here it is denoted by R, if it increases, the type of distribution we assume that tends to follow a double exponential distribution. Here we are showing two cases. One is for the exponential distribution, another is for Gaussian distribution. So when R is very large, it tends to follow double exponential distribution. So if we have a IID data where the data are identical and independent distributed, in that case the values, the theoretical quantiles and the observed quantiles, they follow a linear straight line. However, when we have a long-term persistence, which is in the case of our data, we see that there is a significant deviation from the theoretical distribution and the empirical observation. So this deviation poses a serious underestimation of the risk associated with memory, and correspondingly it affects the design of hydraulic structures. Now the first thing that comes to our mind, what actually drives the memory of stream flow? So in this presentation, the word memory and the long-term persistence will be used interchangeably. So here we can see that when rainfall happens over a catchment, it undergoes lot of processes. It follows subsurface pathways. It also show increase in evapotranspiration based on the availability of energy. But in essence, from the lens of memory, we can see that the memory in the precipitation, which is very low, is transformed to a high memory in the stream flow. So our question comes, what actually drives this partitioning, this from low memory of precipitation to high memory? What actually drives this transformation? So in order to answer that, the first thing that comes in our mind is the input, that is the rainfall, whether the rainfall amount has any significant influence on the memory of stream flow. So for that, what we did is that we have observed rainfall time series and the stream flow time series. We estimated a joint Hurst exponents by detrended cross correlation analysis, and simultaneously we have created the distribution of rainfall where the non-zero values of rainfall are filled with from a distribution by preserving the mean and standard deviation of the original data and the observed stream flow. So we calculated another memory component lambda2 from detrended cross correlation analysis. Now, if the difference between lambda1 and lambda2 is less than 0.5, we can say that the rainfall amount does not affect the joint persistent structure between rainfall and stream flow. If it is not the case, then we can infer that the rainfall amount actually affects the persistence. There is a joint persistence behavior. Now, when we see the case for catchments from MOPEX, which is a data set from US and also from India Kaveri Basin, we see that most of the values are within the boundary of 0.5. So for different cases, like in some cases where your catchment exhibits more snowfall, and there are some catchments in US where it exhibits no snowfall. For all the cases, what we can observe is that the difference between lambda 1 and lambda 2 is much less than zero point 0.5. So this actually hints that the rainfall amount does not actually contribute to the memory of the stream flow. Now the question is, what actually drives the stream flow? So next thing we try to understand whether is the catchment that gives the memory to the stream flow. In order to test this hypothesis, we have taken the rainfall and stream flow time series and computed the lambda 1 like we did in the last case. Then we created a binary rainfall series because we have seen that rainfall amount does not have any impact, and we want to preserve the dry and wet spell structure in the rainfall. So by considering that, we computed lambda 2, which is another bivariate memory component. Now, if the value of lambda 1 and lambda 2 are equal, it means that the dry and wet spell structure, which is preserved in the rainfall time series, that actually controls the persistence. However, if the difference between lambda 1 and lambda 2, there is a systematic deviation, then we can say that the catchment area or the catchment attributes that has more significant influence on the memory of stream flow rather than the dry and wet spell characteristics of the rainfall. So what we did is that we arranged the catchments in an ascending order. From here, the first catchment here is the catchment having lowest catchment area, and the catchment here is the highest catchment area. So when we arrange them in a ascending order, the median persistence is found to be positively correlated with the catchment area. So what we conclude from this figure is that as our catchment size increases, the persistence or the memory of stream flow increases, and this is due to the fact that when the size of the catchments increases, the mean length of the channel that tends to increase. So when there is a more channel length available in a catchment, it provides ample opportunity to the incoming precipitation to get dampened and provide a memory to stream flow. So these are the some hydrological aspects of the memory. Now we want to see how we can give an alternative perspective of the memory based on the principles of complex systems. So in complex systems, we have different properties. Among them, the properties of emergence, self-organizations, and complexity are very crucial component when we are talking about a hydrological system. So the two key concepts which help us in this interpretation are emergence and self-organization. Let us see what these terms are. Now, emergence is an important system thinking concept to navigate the complexity. Emergent properties are often described as more than the sum of their parts because they cannot be deduced or predicted by the individual behavior of individual components alone. For example, the temperature of the gas is an emergent property because it depends the rate at which these gas molecules are interacting with themselves and also with the container. So if the velocity changes, the temperature profiles of the gases temperature is a emergent property. Now, how we quantify this emergence? So there are numerous ways to quantify the emergence. The approach which is adopted here is the use of information entropy. So here we use Shannon entropy. It essentially captures the amount of surprise within a system, and higher the magnitude of the entropy, more the emergence present in the system. And in order to compare different catchments across different scales, we normalize the Shannon information with the maximum possible information, and we define this maximum possible information as this ratio of the information as our signature or the estimate of emergence. Next, next concept of complex system is self-organization. So when a system is designed, simultaneous creation of ordered patterns are formed within the system. In this ordered pattern, the system tend to achieve a intermediate stable state, which translates into reduction in information entropy. So we conceptualize the measure of self-organization as 1 minus entropy, because in the earlier case we have seen that the entropy value can go maximum up to 1. So the remaining part is our self-organization. Now, how to visualize self-organization? So one way of visualizing self-organization is a flock of birds. So when a group of bird is disturbed, they tend to form a bigger flock, a bigger pattern to overcome the nature of predatory behavior by the organism which want to attack that bird. So this is one of the survival strategies of the birds, which is a good example of self-organization. Now, how these concepts of temperature of gases and the flocking of birds, how these concepts can be utilized in hydrology to understand this memory effect. So before going to that, the last component of a complex system is complexity. So what it does is, complexity actually measures the balance between the emergence and the self-organization. So it is given by a product of emergence and self-organization, E and S. So in this formulation, it can be seen that the complexity value lies between 0 and 1. It can be only 0 if E and S is 0. That is, our system is completely deterministic. And E will be 1 when our system is, when we have an entropy at the midway, that is 0.5. So basically, the complexity versus the state of the system is look like this. So a system which is completely disordered, it has a very low complexity, and a system which is very ordered, it also has a very low complexity. However, the system which lies in between these states, they have very high complexity. Now we will look where our hydrological systems tend to stay in this axis of the orderliness and disorderliness. The probability distribution function of streamflow can be conceptualized as the integral signature of the interactions in the complex catchment system. For different types of catchments, in terms of soil, vegetation, and climate, the probability distribution of streamflow will be different. In this case, we have considered 385 MOPEX catchments from US. The catchments are classified into two groups based on the fraction of precipitation falling as snow. The value of that fraction is taken to be 0.15, which means that 15% of the precipitation that falls on these catchments are as snow. The selection of this 15% is based on the fact that the effective contribution of snow in runoff generation is only noted when the value exceeds 15%. And the dominant land cover and the soil type in these catchments are given by this acronym. Now let us see how, for these two classes of catchments, the complexity of the stream flow varies. These templates show the relationship between the complexity of stream flow with dominant land use and land soil type for two classes of MOPEX catchment. A dot in this template represents a single catchment with a complexity value for specific combination of vegetation and soil type. For example, this highlighted portion, we can see that it is a combination of evergreen broad forest and silty type of soil. So similarly, in the second class of catchments, where fraction of precipitation is more than 15%, here also we find the similar vegetation and soil cover and the soil type. And what is interesting to note is that even though we have similarity in soil and the vegetation type, there exists quite a bit of variability in the values of the complexity of stream flow. For example, the catchments which are located in high snowfall region, they have very high complexity in compared to the catchments which are located in the low snow region, although they are having this similar vegetation and soil type. Now, how this complexity is a function of climate. Like soil and vegetation, the long-term hydroclimatic conditions play an important role in the behavior and response of catchment systems. The hydroclimatic conditions are represented using aridity index, which is a ratio of long-term annual potential evapotranspiration to annual precipitation. What we observe is that a significant negative association between the complexity of streamflow and the aridity index. The strength of association is more in the catchments with low snow fraction. However, when the aridity increases, the increase in aridity implies that more energy is available for which provides opportunity for evaporation, and as a result of that, uh, the lower fluctuations is shown in the streamflow behavior. So, as a result, the entropy of the streamflow tends to decrease, resulting in lower emergence and high self-organization with increasing aridity. The most important aspect of this study is to find a relationship between the memory component, that is the Hurst exponent, and the complexity. So what we find is that in both the cases, the Hurst exponent is positively correlated with the complexity. So what this suggests is that how complexity, which actually measures the balance between the information generation and the self-organization structured in our stream flow, that actually this balance of information generation and stability structure in a stream flow pattern, that actually give rise to the memory of the system. And this is what we infer from this scatter plot. And we observe this correlation to be significant. The scatter in this correlation in this plot is due to the fact that these catchments are widely distributed across different climatic zones within the US. So there is a scatter. However, there is a significant association between the complexity and the memory component. Now, this complexity, the entire process happens under a causation. There is a level of hierarchy from the source to target system, and the causation, this information exchange passes from the sources to the target variable via different hierarchy of the system. So the determination of the causal structure is one of the crucial aspects of any complex hydrological system. This structure can be determined by analyzing the system from causal perspective. However, in Earth system science, it is very challenging task to identify appropriately what are the source variables and their influence on the dynamics of target variables. The challenges can be broadly classified into three groups, which can be related to the process, data, and the computational or statistical aspect. Other than these challenges, the choice of causal discovery methods are equally challenging. In addition, the presence of long-term persistence in the hydrologic processes, the inference from these causal discovery methods may not be appropriate for identifying the source and the target variables in a complex system. So, in order to test the efficacy of the conventional causal system, two experimental setup has been done. First one is synthetic system, another one is real-world precipitation streamflow transformation. So, and the three causal methods which are popularly used in hydrology and other earth system sciences are used. They are Granger causality, transfer entropy, and causal decomposition. So, in the synthetic system, we have devised three types of source structure. First one is the first source variable we generate in anti-persistent system. Then we generate a random system, and then we generate a positive persistent system. Now, these three classes of source drivers is fed into a simple bivariate model, which has two components. One is the autoregressive component, which is the dependence of the present value of the system to its immediate past, and also we have a coupling of another variable in this bivariate relation. So when we fed these classes of source variable in this model, we get three different types of target variable. Now we have simulated this using RFIMA system. So RFIMA is auto-regressive fractionally integrated moving average system, where in which we can actually simulate time series by keeping a specific Hurst exponent. So this is how we have generated this synthetic system. And in real world system, we have taken the same catchments, which is classified into two groups. And the transformation process we are considering is the rainfall streamflow transformation, or the rainfall streamflow causality. Now let us see how the performance of transfer entropy, Granger causality, and causal decomposition method is affected by the presence of the state of memory of the source variable. Now here there are two plots. The first plot is showing the true causality. That is, actually we have made the system in x2y, and we also fed this causal structure to the causal discovery methods. And in the other case, we have prepared the system from y to x to y, but we fed the causal methods as y to x. So this is a false causal system. So we want to see how this true causality and false causality discovery is affected by the level of persistence the process has. So this heat map, each and every heat map, it shows different states of source variable. So this row shows that the state of source variable is anti-persistence. This is the random process, and this is the positive persistence. So this x-axis of this heat map shows the state of persistence of source variable. The y-axis shows the strength of autoregressive parameter of the bivariate model. So what we actually can see in this diagram is that the method of causal decomposition, that is CD. So these three rows are for three methods. So this is for Granger causality, the middle one is for transfer entropy, and the last row is for the causal decomposition. So the method of causal decomposition detects two direction of causality in most of the cases for different combination of model parameters. GC, that is the Granger causality, it also able to detect large number of true causal direction, and also the how many causal groups it will detect depends on what is the strength of autoregressive parameter, and also what is the strength of persistence within this source variable. Surprisingly, what we found is that the transfer entropy is doing the poorest performance in this case when the source variable is undergoing three different states of memory. So this is failing in this case. Now, when we go to the false causal discovery method, like when we flip the causal structure, what we find is that causal decomposition, that is CD, it actually detects less false detection than other methods. Other methods in like Granger causality and the transfer entropy. So essentially, what we can infer is that causal decomposition method performs better than Granger causality in detection of the true causal direction, while the source variable is in the state of anti-persistence and random. The model parameters affect the detection of the true causal direction in both Granger causality and CD when X is in the state of positive persistence. However, the transfer entropy method is unable to detect any true causal structure, although it detects minimum false direction in the causality. So these conclusions are only what we concluded is only valid for the bivariate linear systems, where the state of persistence in the target variable is dependent on more on both model parameters as well as the persistence of the source variable. Now this is the case for synthetic, what we call the synthetic experiment. Now let us see how the real world example takes place. So what we can see here, these are the cases of the performance of three methods for two classes of the catchments. And the first row shows the detection based on the true causal method, where we maintain the causal structure, and this is where we flip the causal structure. And we are trying to see how many false detections they are able to see. They are able to detect. So the method GC, transfer entropy, and causal decomposition are actually finding. So among this, the Granger causality is actually having is showing the high number of true causal signatures rather from transfer entropy and the causal decomposition method, whereas CD, that is the causal decomposition, detects least at the monthly scale. So here we perform this causal analysis in two scale, that is a daily scale, another is a monthly scale, and in that Granger causality is performing much better than transfer entropy and causal decomposition. Now when we flip the system, what we find is that at daily time scale, transfer entropy is showing high detection of false causality, and in monthly scale it is showing very low detection. So it is kind of sensitive to the time scale of observation and also the state of persistence of the source variable. So what we can conclude from this study is that the efficiency of these methods can be justified if we consider both the structure of memory in the causal variables and also the time scales in which we are considering. One of the reason why transfer entropy is showing very high false detection in daily case, it can be due to the Markovian structure of dependence in the target variable condition on the past variable, past of the source and target variable. So that partitioning, that is that Markovian structure, is actually hindering the performance of transfer entropy in this case. Now, at the last of the presentation, we want to understand why this memory, how this memory is actually organized or it is created. So, in the system of theory of dynamical system, let us consider a coupled linear system in x and y, where x dot is defined as the differentiation of x with respect to time. Given the initial condition of the source variable, we can express the dynamics of x in terms of y by replacing the x derivative with yt. So yt is the solution of these two differential equations, and we replace yt in the first equation. So the final equation is actually how the temporal evolution of the dependent variable or the target variable is dependent on three factors. So this is the first factor, L11x, this is the second factor, and this is the third factor. Now let us see what these factors actually represent in real world. So the first factor, L11x, this is the Markovian term. So what does it mean? It means that this Markovian term controls that the current state of the system depends only on the immediately preceding state and not on all the other states in the distant past. The second term, this is actually the memory term, because it integrates the process from the beginning of the system. And the last term, this is influenced by the initial condition of our source variable, that is y naught. So what essentially we are doing is that the transfer entropy is actually capturing this part, but these components are missing in the formalism structure of transfer entropy. And moreover, in our hydrological system, what is happening is that most of our measurements are point measurements in a continuity, in a field continuum. We are just taking a point, or which are essentially the subsets of continuous field. In either cases, their dynamics came from a low dimensional system embedded in climate system of infinite dimension. So this Morris-Zwanzig formalism, which actually partition the dynamics of the source variable, it shows that memory is only one component of the entire dynamics of target variable, and our conventional causal detection methods is only capturing, most of the time it is capturing this Markovian structure, and very little the focus has been given to this memory term, which is again it is assumed how this memory term is decaying, whether it is long term, whether it is decaying in an exponential term or it is decaying in a power law fashion. So these are the some sources, these are the some implications of this dynamical system, which may be incorporated in the causal detection system so that our causal methods can work much better when our system is severely influenced by memory. So the important take-home messages from this presentation is that the persistence of the rainfall and stream flow are not controlled by the amount of rainfall. Larger the catchment size, more is the persistence of stream flow. The complexity, which is actually formulated as a balance between information generation and self-organization, that actually captures the long-term persistence or memory of stream flow. And the performance of the conventional causal detection methods is influenced by state of memory of the causal variables and the autoregressive parameter, and the Morris-Wanzek formalism, which actually decompose the dynamics of target system into three components, can actually hint how we can improve the conventional causal detection methods so that we can apply this method in the system which is impacted by the memory. Thank you for listening.
Thanks a lot, sir, for a wonderful presentation. Let's, if there is any question from participants, you can unmute and ask directly. Otherwise, you can also write in the chat box. Oh, yeah, Tejasvi, you can unmute and speak.
Hello, am I audible?
Yeah.
Yes, Tejasvi.
Hi, Pankaj. It was a very nice talk. Thank you so much.
Thank you.
I want to know more about these concepts. So, I mean, my doubt is in slide 7 when you talked about distribution of P leads to a distribution of Q discharge, right? At some point here, precipitation leads to a distribution in stream flow. Would you say that I want to link here? You said that there is a presence of memory. That's why the spread of the distribution of stream flow increases, right?
Yes.
So I wanted here to know what could be the link to information theory here, because precipitation's distribution are narrower. So I would personally understand that they have very low information, low Shannon's entropy, and presence of memory changed this distribution into a high spread distribution. So higher information, right?
Yes, what actually
would you say that means? Am I understanding it correctly?
So you are saying that information in the precipitation it is there. So information, what this figure is showing is that most of the precipitation has low to very small memory. Okay, so when this rainfall is interacting with catchment system, we see a wide range of memory in the stream flow. Now, what actually drives this spreading? That is your question, right?
Yes.
So this spreading, this memory is entirely a function of the catchment. It is not what this study actually found is that this spreading is entirely the role of the catchment, not the rainfall. Whatever the rainfall is, you only can use the this is only a function of catchment, not the climate. That is what we have deduced.
Okay. So this is Hurst exponent plotted, frequency of Hurst exponent. That's what you have plotted here, right?
Exactly.
Okay. That's nice. I wanted to understand what's the link between persistence versus at some point in last slide you said that can you go to last slide?
Yeah.
Where you laid points.
In this one?
Where you summarized all the points.
Oh, okay, yes.
Yeah, this one. So larger catchment size leads to persistence in discharge, means higher Hurst exponents, right?
Yes.
But then we argue that physical settings of soil, vegetation, landscape lead to complexity. So
yes,
complexity should also be related to persistence here, right? The plots that you showed of role of complexity measured using soil properties and etc. They could, in principle, also be made using area discharge relationships. That's
So
what I
which
was thinking.
one?
How is persistence related to complexity here? Because
Yeah. So
here we say that you
yeah,
measured complexity as a function of vegetation properties. Did you get my question?
yeah, I got it. So
But same can
what?
be also made using area discharge relationship.
Which one? Complexity?
Yes, I mean that's what I wanted to know, because first you explained that persistence in discharge is a function is decided by catchment properties like area of catchment, which we
Yes.
also study something called Heck's law, the area discharge scale
Yes.
relationship.
Yes.
I think that would
Yes.
be what emerges out of this relationship. But
Yes.
then we say that complexity of stream flow is a function of other properties like vegetation, landscape properties. So if, I was wondering if have you considered area of catchment here as a driver of complexity,
Complexity.
or yes?
Yeah. Yeah. I actually have that. Let me show. Let me show that slide where it is. Let me check. Actually, this complexity and also have some relationship with area of the
Okay.
what you call this catchment. So unfortunately, I do not have that slide, but yeah, I remember I also plotted that. So there is a relationship that is also positively related. That is, complexity is positively related with catchment area. Unfortunately, I do not have the slide currently with me. That is there. Yeah, that is related. Yeah. So what essentially we
Okay.
are showing is that we have two things. One is your persistence, which is a purely stochastic component, which we explain in terms of decaying or water correlation function. Now, what
Yes.
complex system is showing, it gives a more richer definition of persistence. That is, complexity. The way we defined here is it measures the balance between information generation and how much of that information is used to generate stable pattern, that is predictable pattern
Okay.
in stream. So that balance is actually measured by complexity. Now, what we found is that this complexity, value of the complexity, is proportionately equal to the value of our memory or the Hurst exponent. So this actually provides from the autocorrelation function, which is a univariate signal, we get a
Mhm.
much more comprehensive interpretation of memory, which is a function of complexity, because complexity is a function of all the integrated processes that is happening in a catchment.
Okay. I mean, I think I'm sorry if I keep asking repeatedly. Avinash, you can stop me if someone else raises his hand and we can ask the question further. But what I understood is that perhaps for an intermediate number of value of Hurst exponent, you should get maximum complexity. Shouldn't it be true? Because in the scatter plots where you showed on x-axis there was complexity, on y-axis there was Hurst exponent, and you said that maximum value is 0.5 for complexity. At 1 also we get low complexity and high also, something like that, right?
Complexity, yeah, I think complexity, it is going from in the range of, let me share that. It is going up to 1, like that is the highest value. Let me share my slide.
When we do 4 times E minus S, 4 times emergence
Yes.
minus self-organization, this is on x-axis, right now.
Yes. Yes.
So this has okay. So highest value of complexity is 1 here. That's what
Yes, 1.
you're
Yeah,
saying.
1. Yes.
Okay. I thought it's 0.5. Sorry. Then higher Hurst exponents lead to higher complexity then.
Yes, that is the inference.
Okay. This is very interesting. Yeah. Thank you.
Okay,
If
there
anyone
is
else has a
a
question, they can ask. Otherwise,
yeah.
yes.
There's a question in the chat. I suggest Balaram, if you can able to unmute, you can ask the question yourself. Is it possible? Okay, actually the question is a little long. I mean, he asked multiple questions. So I'll just question one by one. First he's asking, what do you mean by simulated and binary rainfall and stream flow, and why do you use those? I think he's talking about in the beginning slides where he compared, persistence with binary and some simulated rainfall, right? So,
Okay. So yes. So what we actually found is that it does not matter whether what is the actual rainfall observed corresponding to the observed stream flow. If we change the values of the rainfall just by keeping the structure of dry and wet spell same, if you just replace the value with some other values, keeping the distribution of the rainfall same, it does not necessarily impact the persistent structure. There is a joint persistence structure. So in order to show that it is the catchment property, the persistence in the stream flow is only the catchment property, not the property of the stream flow. Sorry, not the stream property of the rainfall. We actually converted, what we did, we actually put the wet spell values to 1 and other dry spells all are 0. That is, all zeros we kept intact and all the rainy days we replaced by 1, because even if we without replacing 1, even we can take any other values, the inference will remain same. The thing is, the joint persistence between rainfall and stream flow, that is only driven by stream flow, not the memory of rainfall. That is the main thing.
And second question, I think you already covered. He's asking why to use a synthetic system for analysis when you have the observed data.
Okay, so in synthetic system we have more control. Like you can simulate. We can simulate our source variable into anti-persistent, into and random process, and also positive persistent. But in natural system, we will only get something between random and positive persistent. So we won't get the entire spectrum of the possibilities that can happen. So when we are under a simulated system condition where we know actually just two variables are there, how they are interacting, we know the causal structure, then we try to first see how this theoretical condition, how well our causal methods are able to get this causal structure, true causal structure. So we see that it is a function that the efficiency of this method is a function of this memory, autoregressive parameter, and the coupling between the source and target. This P actually controls here in the simulated system. So similar kind of concept will also be there in our real world system, but there we do not have a control on the target variable. So that's why, to see the full spectrum of possibilities that can happen in their performance, we have used a synthetic structure.
Yeah, I think the third question is also answered. The fourth one is like, do you think only the catchment area will influence the long-term persistence?
Catchment area is one of the factors. There are multiple theory, like, because this catchment area and the channel network, these are actually a function of optimal organization. That is, optimal organization or the optimal use of the mass and energy that is available. For example, if you look at a dry catchment or the catchments in an arid region, they tend to be more wider. Okay, and the catchments which are in humid region, they tend to be more shallower or more narrower. So catchments which are in in humid region, they do not want to lose water in the form of evaporation. So that's why their entire shape of the catchment is different. Let me show this slide. This is a very interesting point. I have this with my presentation. So the shape of catchments, that is also a function of your complex system. This complex organization principle. So here, if you can see, these are the two plots. Okay, so first one is for the arid catchment and the right one is for humid catchment. So arid catchments are mostly self-similar. Self-similar means if you have a drainage network like this, if you zoom in, you see the same pattern. However, when the system is in humid region, we do not have a self-similar pattern. Okay, so what is happening is that at small scale, humid basins tend to grow in response to mostly diffusive groundwater field. However, at a larger scale, both arid and humid networks, they act similar. That is, they want to collect water and they want to minimize the loss of water. So this growth of river network structure, this is actually is a result of self-organization over a long period of time. So this actually shapes the size of the catchments.
And he's also asking about what do you mean by fractional integrated in Arfima model?
Okay, so ARFIMA is, so we know ARIMA model, right? Where the mode of integration is integer, it is not a fraction. So when we want to include memory, we need to do a fractional integration. So it lies between 0.5 to plus minus 0.5. Okay, let me show that slide here. So this is the actually this G, this G is actually integer in case of ARIMA system, but in ARFIMA this D is a real number. Real number means it lies between minus up to point five. So if you want to simulate system which has different state of memory, you need to use ARFIMA system, which is a broader class of fractional Gaussian noise system.
I have one question. I mean, which is
Sure.
in terms of extremes. So basically, in India, let's say like I mean, a lot of regions have flood. It's caused by sudden cyclones or kind of high precipitation events. So there, I'm just curious, what's the influence of persistence?
Yeah, in India, what we see we have most of the rainfall in 4 months, right? So the system is highly seasonal, and our most of the floods that happens in India is within these 4 months only, July, August. Maybe in the southern India, it may delayed because northeast northeast monsoon is there, which comes in winter. So how persistence is impacting? Of course, the persistence is there because if you take this spell of wet, this wet spell over longer period of time, and you try to see, you just plot the autocorrelation function of this rainfall or the timing of the floods, you will see that that autocorrelation function is decaying in two ways. It can decay in two ways. First one is, if it decays in an exponential way, you cannot say the system is long-term persistent. It is a short-term persistent. Okay, what does it mean? It means that next value or the future value is only dependent on to a certain value in the past. But when your autocorrelation function of that variable is decaying in a power law fashion, there the next value or the future value is dependent on all the values of past. It is not up to lakh 10 days or lakh 20 days. It takes all the values of past. So the main difference is how your autocorrelation function is decaying, and that drives your persistence, that drives your memory. The most elucidating thing is that often this long-term persistence is modeled by short-term processes. For example, you can model the AR1 using AR1 model to model the decaying of the autocorrelation structure. So that will have very significant impact when you are designing your return levels. For example, the value of this persistence thing has find more importance in drought management. And what one of the study has found is that if you use this short-term memory or AR1, which is capturing the memory, you will get a return period of 500 years. But when you use this ARFIMA system, which actually takes care of the long-term persistence, then your risk comes to 100 years level. So there is a 5 times difference in the risk estimation. So how you are
So,
actually modeling this, that is actually very important.
so you're saying like without Arfima, we are underestimating.
We are underestimating, yes.
Okay. I have one more question. So you mentioned about this flood. Okay. I just missed. Okay, maybe I will once I get back. I will ask if someone else have. Okay, yeah. Now I got it. So, so the thing is, so you were saying like persistence is mainly due to the catchment properties, but there's also, I mean, personally, I feel like there might be some rainfall characteristics which could play. Like, let's say, like there's a difference between the sudden high intense rainfall versus a long-term low intense rainfall. Uh, so rather than it's obviously there's a catchment has a role to play there, but it's also about the characteristics of rainfall, isn't it?
Yes, exactly. So what I said is that rainfall amount that has no role in persistence of stream flow. However, the patterns, that is how this long-term patterns of your dry spells and wet spells are there, it is rainy days and wet days, that pattern is important actually. So in my analysis, we are actually preserving that pattern. We are just only changing the values of the rainfall to ensure that rainfall amount has no influence. But the pattern, how many days it is raining and how many days it is dry over the longer time, that has an impact. However, that impact, I have not analyzed how much of that impact comes to the memory of stream flow, but I believe that impact will be much less than the organization principle of this catchments. That is called theory of self optimal use of materials, which we have in scale invariance theory.
So, and also I have like one more, it's not a question by the way, but I mean, you're talking about the snow influenced regions, right? Like you differentiated two regions. So let's say like snow dominated regions, there obviously catchment has a role to play everywhere. But there is also like, the climatic regions, right? I mean, more than the catchment, climatic region has a role to play in the snow dominated region, right? So, because that denotes when the snow will be melting. It will be dictated mainly by that.
Yes, exactly. So the snow melting that also impact the memory, like right, because it depends on how much snow, how much sunlight is there, how much energy available is there, what is the exposure length. All these are the factors that actually govern the snow melt and that contribution to stream flow. So what we found for this regions with very high snow, persistence are very strong. That is, the flow is more smoothened. Our system is more, the system is very close to 1. The value of Hurst exponent is very close to 1. That says that we can be very sure the autocorrelation function decays in a power law manner. And that is, in such cases, we can say that it does not matter what is the value of the precipitation that is falling there. It is the dynamics of the snow that actually controls the persistence. Yeah. So you need to take care of this distributed things, distributed components like energy and all. We need to go for like more in a modeling, distributed modeling framework, because here it is mostly empirical. We use statistical tools to discern this theory. But if you want to see, like for suppose in a snowy region, if we have 10 hour of daylight, how 10 hour of daylight, how the persistence will impact. In such case, we need to go in a more distributed framework model rather than constraining us in a stochastic model. Yeah.
Right.
I have one question. What should a curve between Hurst exponent and Shannon's entropy look like? What do you think?
Yes, I have it here. Let me.
If I'm understanding correctly, then high Hurst exponents should lead to low Shannon's entropy, because everything is dependent on the past, so there is nothing new to be.
Yes, I am showing that. I have exactly that slide. So this figure, you see here, this is the probability of 0.5. So if you look, this black line, this is your Shannon entropy, and this red line is your complexity. So high Shannon entropy is low complexity.
Okay. Low complexity means high Hurst exponents. Yeah. It could be low Hurst exponents as
low
well.
Hurst exponent, low Hurst exponent, yeah.
I mean, high also would lead to complexity is a function of means complexity has a maximum value at intermediate values of Hurst exponents, right?
Yes.
It's self-organization times emergence.
Yeah, so complexity will be maximum when E and S are 0.5.
Yes.
So that is so when entropies are in the mid range, then we expect our memory to be very high.
Okay. I see. Yeah, I got it. Thank you.
Actually, I also recently published one paper in HES where actually we use complexity and entropy and the time scale of function, like time scale of force graining, to classify different types of systems. Like suppose if your system is driven by snow, how the profile will look like, what does this area under the curve represents actually. So I published a paper on that. So that actually taking this idea of complexity to system identification, so that we can identify system whether, like, suppose a system has severely human condition, like conditioned by human activities, how their behavior in complexity plane will differ, how to identify that. So we have devised a rule on that, and we have a paper on that. You can look at that.
I think you're talking about the complexity uncertainty curves. That
Yes,
paper,
CU curve. Yes,
or
CU curve.
is
Yes.
it something different?
Yeah, it is CU
Yeah,
curve.
CU curve.
Complexity
Yeah, I know about that. Yeah. Thank you.
And is there any question from participant side? I don't see anything in chat box. Okay, if there is no, then let's end the webinar here. And thanks a lot, Dr. Pankaj, for a wonderful presentation and linking all the complexity in catchment characteristics. It is highly needed and it's new to I mean me. Maybe it's also new to a lot of people here. And once again, thanks and thank you everyone for attending this session. And happy weekend. We will meet in the future webinars.
Thank
Bye.
you. Thank you, Avinish.